Hey guys, okay, today we're finally gonna go over the I2C protocol on the STM32. Um, this little blue pill or that big blue pill. These are both the same chip. That one just has more pins, more memory and stuff like that, but it's still the F1. So yeah, I'm gonna go over the I2C integration for the STM32 F1 series, which is slightly different, uh, and not in a good way, than their newer chips. I highly recommend trying out their newer chips like the L0 and the G0, or some of the F4 chips or the F3 chips. They have a much nicer implementation and much easier than what you're gonna see here today. Um, if you do want to check it out, I did a little write up for that on my blog, the I2C for the L0, and you'll see how great that thing is to work with. Anyway, so let's get on with this. First things first, you're going to need, well, actually, you don't need it, but it helps if you have some sort of logic analyzer. Um, there's this company, Sally, or I'm not sure how you pronounce that. Then there's your cheaper ones that you can get on Amazon for like $11. And I will be honest with you, I'm using this one more. This one costs like 150. But the software that I use for this one, I just like it. It looks so much better. This one, I don't know. Maybe I'm just bored of it. This one is, I got it with a student discount. So if you have a student ID, or you know somebody that goes to college and they have a student email, you can probably still get these. The difference between these student versions is that, one, it doesn't cost $800 like the other versions that they have, and it only has 4 channels, not 8 or 16 like their more pro versions. But like I said, I haven't used this in a while. I use this one more just because I like the Pulse View software. This is basically a clone of this, because when you open up the software for this guy, it says Sally Logic, so it's basically a clone of this one. Another thing you're going to yeah, you don't need those, but it really does help. And I'm gonna post a link for this one that I have. I think it was 11 or 12 bucks on Amazon. And yeah, it'll be an affiliate link of mine from Amazon. Again, you're not going to pay more, but Amazon will kind of give me, some points for sending people over, so then I can buy more stuff. You're going to need a calculator, definitely. So yeah, that's it. And I'm going to go ahead and get into the data sheet now, and we can start talking about this I2C stuff. Oh, another thing, obviously, you're going to need something to talk to. Okay, so you can go ahead and maybe if you look, uh but I mean, if anybody really wants that, I can go ahead and cover that in another video. Right now, I'm just gonna show you how to transmit to a slave device. So yeah, I'll post the link there, maybe for like a cheap EEPROM, something with like a dual inline package that you can put on a breadboard. Anyways, on to the data sheet. Alright, I2C, I2C, whatever you want to call it. I'm not gonna go over the protocol like I don't go over the protocol for any of my tutorials, because there's plenty of videos on that. This is strictly on how to get it working on the microcontroller here. So I'm not gonna tell you about the timing and this and that. You know, unless you're interested in implementing it in a in an FPGA or something, it's really not. You don't have to fiddle with any of that. So yeah, this is the block diagram for it. Again, it's not really anything out of this world. One of the things you should notice is that there's these data shift register and the data register. So the data register is like any other peripheral here. That's where you're actually gonna write your data to, and that's where you're gonna get your data. And then this shift register is actually, that's where your data arrives, right? And then it gets shifted to the data register for you to read. So let's say you received a byte and it's already in the data register. You could already be receiving another byte and it'll already be in this shift register before you've even read this byte. So the second you read the byte that you received that's in here, then this one will get shifted into here. Okay, so that's a little something to take note, because there's a weird condition, something that goes on, I guess a little erase condition in the I2C implementation here, where that if you don't read these two fast enough and generate a stop condition, then the I2C will end up getting more data than it should, or your data will be corrupt, or you'll get a bunch of weird messages, and it's terrible. It is in fact a race condition, because you have no idea how fast the chip that you're talking to is sending the data. So if you don't do a certain action before it happens, you get bad data. So that's why and that's only for the RX of the I2C. So that's why the way I'm going to teach it in this tutorial, we're going to use it using the DMA controller, where you don't have to worry about anything. You just tell the DMA controller how many bytes you're waiting for, and it's gonna do it for you, and that's it. Easy peasy. So yeah, there's all kinds of stuff here. If you really want to read it, you can by all means go ahead. I'm gonna just jump into telling you about the registers and what the bits mean and all that great stuff. Okay. Oh, another thing to notice is that some of these bits in the registers are not necessarily for the I2C, because in conjunction with this I2C peripheral, they've integrated another bus that is, I guess it's similar to the I2C, similar enough where they've implemented them, I guess, one on top of each other. This one, it's called the SM Bus. All right, it's a 2-wire protocol, 1 clock, 1 data, just like the I2C. But I guess it has some differences, and I haven't read up on it, so I'm not gonna cover that here. So yeah, some of the bits will apply to the SM bus. So we're not gonna use this peripheral in SM bus mode. We're gonna use it in regular I2C mode. Another thing I want to mention, since we're gonna use it, is the DMA requests. So yeah, it has DMA requests. We're gonna enable them, and then I guess I'll show you how it works in the code. And once you see the code and how it works, I'll come back and explain to you what the data sheet says. Packet error checking, again, this is not necessarily for the I2C. It's more for the SM bus stuff. Then there's interrupts. I'm not gonna use interrupts in this tutorial again, because I am gonna be checking the flags. I'm just not going to actually implement the interrupts. And I recommend almost exclusively, always, any chance that you get, use DMA, especially with this I2C peripheral, since it's so crappy in this F1 chip that came out a million years ago. Okie dokie. Control register 1, bit 15. This simply puts it in, this is I guess a software way of resetting the peripheral. if you get stuck in because it does get stuck in this busy, it's I guess some sort of bug in the hardware. If it gets stuck in busy mode or any other state, you can come here, you set this bit high, and it will reset the peripheral. Okay, 14 is reserved. 13, alert. This is an STM Bus related bit, not concerning to us. This one is also STM Bus, this packet error checking bit. That's not related to us. This POS and ACK bit. So that's the next page. Alright. Before I explain the POS, I have to explain this bit. So this bit is the acknowledge bit. This is how you control what you do when you receive a byte. Right? So if you're watching this tutorial, I hope you've previously watched something explaining the I2C protocol. So when you receive a byte from a slave, like an EEPROM chip, for example, and it sends you over some data, you can acknowledge it or you can not acknowledge it. To acknowledge it is you're telling the chip, okay, I got your data, send me more. So you acknowledge it, it'll send you more data. If you do a no acknowledge, then it stops the communication. So this bit right here controls what you're sending to the slave every time you receive a byte. So if you have a 1 here, then every time you receive a byte, you're going to send it an acknowledge. Until you receive the number of bytes that you want, then you're going to set this bit to 0 and you will send it a no acknowledge. Okay? Simple as that. However, this POS bit modifies this in the sense that when this POS bit is 0, then these settings, these acknowledged or not acknowledged, apply to the current byte being received in the shift register, not in the data register. Remember, in the shift register. So that's by the time you read your data from the data register, there could already be something in your shift register. Okay, you don't really know. So that's why this implementation of this I2C thing is terrible. Anyways, so yeah, this controls the ACK or the NAC. So if this is 0, right, that means that the current byte in the shift register, then after that byte in the shift register, you will send either a NAC or an ACK. However, if this POS bit is a 1, then these settings, ACK or NAC, will apply to the next byte that comes in the shift register, as if you somehow gonna know that, right? So yeah, that's basically what it does. So either you apply these settings to the current byte in the shift register or the next byte in the shift register. That's all this does. And there is an entire annoying method to receive data. There's a method to receive just 1 byte. There's a method to receive just 2 bytes. There's a method to receive more than 2 bytes. And once you get down, let's say you're receiving 5 bytes, but once you get to that 3rd byte, you have to enter the receive 2 bytes mode. And then once you get down to 1 byte, you have to enter the receive 1 byte mode. It's disgusting. And when you use the DMA, you don't have to worry about any of that crap. This explains all the things you have to do in the different modes that you're going to receive the data. I'm not going to go over it. You'll just throw up and quit. I gave it a shot. It was terrible. It worked sometimes. Sometimes it didn't work. There was these race conditions. This is the race condition right here. It says, the event 7 software sequence must be completed before the end of the current byte transfer. So before I transfer my current byte, I have to complete this event 7. Which says that I have to clear the R, X, and E by reading the data register. So I have to read my I have to read the current byte before I get the next byte in the shift register. In case EV7 software sequence cannot be managed before the current byte transfer, it is recommended to use the BTF instead of XD, blah 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 blah. Trust me, you don't want to worry about that. I'm not even gonna keep talking about it. Alright, so my wife texted me. The stop bit is bit number 9. this is how you end communication in I2C, right? So if this is a 0, stop texting me. If this is a 0, you're not generating a stop bit. That means your communication is ongoing. If you put a 1 here, then you send the stop condition on the I2C, and there it is, and basically the stop condition. Here are acknowledges, right? As you can see, with every acknowledge, I get more data. And then P, I'll show a zoomed in version of this. P is let me go into that mode right there. Where are we? Here you go. P in this software, P is the quote unquote stop condition. Alright, we'll get into that, so no worries. Where are we? Okay, so back to this. So that's our stop condition, and then this is how we generate our start condition. Obviously a 0 is no start condition, and then a 1 generates a start condition. You can generate a start condition and, you know, do some communication, and you don't necessarily have to stop. You could generate another start condition. So yeah. Clock stretching. Clock stretching is important. Clock stretching allows just what it implies, the clocks to be stretched low. And that's important because if you're communicating to let's say you're talking to an EEPROM chip like I am over here, and I'm using I2C, and you know it's relatively fast. Then if I'm telling it commands to write this and write that and all this stuff, it cannot keep up. It needs time to actually do the writing, the actual writing of data, of saving the data into its memory. So then you have to, how do you know when it's done writing? You really don't. What you do is you enable clock stretching. That enables the slave to stretch the clock low. What that does, it's almost like it's pausing the communication until it lets go of that clock stretching, and then the clock continues, and then the communication continues. So you definitely want to keep this clock stretching enabled, especially if you're talking to a chip that's slow, like a sensor or EEPROM, things like that. General call enable. This is basically if you're a slave, and this here too, this applies for slaves, but nevertheless you should always enable clock stretching. Shoot, where am I going? General call enable. If you're a slave, and then the master sends out the address 00, you can reply to that address, right? Even though it's not your actual slave address, you can reply it. So it's just a reply to it. It's just a general call. You can use it, for example, if you're a slave, to it's kind of like taking attendance or taking roll. Like if you have a bunch of sensors and you send out a general call, they can all acknowledge it, and you can kind of get an idea, I guess, of how many sensors you got and things like that. These are for the SM bus, not related for us. SM bus. And then, okay, well, this one definitely you want to keep it at 0. That means we're using I2C and not SM bus, right? And this doesn't concern us. And then this bit eventually does enable the peripheral. Okay. Sorry I did go on a little rant there, but we just went over control register 1. So our reset, these things don't apply to us. This is some annoying thing, and here's acknowledge, stop, start. You want to enable clock stretching. This is the what is it? Oh yeah, enable general call. This doesn't apply to us, and this doesn't apply to us unless you leave it at 0, which means I2C. Oh no, that's this one, SM bus. Yeah, bit 1. All right, register 2. What do we have here? This has to do with DMA. This is you're telling it whether the last transfer of the DMA is indeed the last transfer of your entire I2C communication, so it can end it or not. So you can set it that it's not the last transfer, or that it is the last transfer. This enables the actual DMA. So DMA request disabled, or 1 DMA enabled when TXC equals 1 or RxNE equals 1. IT buff and ITV and these three right here, they enable interrupts. So this one will enable the buffer interrupts. So this will tell you when you transmit when you're ready to transmit the next byte, or when the you're ready to receive the next byte. And then obviously one will enable those two flags, the transmit empty and the RX not empty. This enables the different events that happen. So obviously when you're starting a communication in I2C, the first thing you do is you send a start condition. Once you send that start condition, you got to send the address so you can find the actual slave you're talking to. Once the address finds a match, then you can start go ahead and proceed with your RX or TX, whatever it is you're going to do. So these events right here will happen. For example, SB equals 1. So when you send the start condition, you have to wait until it actually sends it. You can't send the start condition and then right away send the next address, because remember, this microcontroller, the F1, is operating at 72 megahertz. So when you send that start condition and you start writing the next address and start sending data at 72 megahertz, there's no slave that's going to keep up with you. So you have to wait. This flag right here will tell you that or this event right here will tell you that the start bit was successfully sent. This one will tell you that there was an address match. This is for 10-bit addressing mode. This one tells you that there has been a stop condition generated. This one tells you byte transfer complete, which is kind of similar to this, to the TXT empty. This is the RX not empty event, which tells you that you received data, and this one tells you that you are ready to send data. Interrupt error, this tells you there's been an error, and there are all these kind of errors. Arbitration lost. They are defined up here somewhere. Of course, I'm not going to find it. Anyways, they're up here. You can find them. Error conditions. Here they go. Bus error, acknowledged failure, arbitration lost, overrun, things like that. Overrun error simply means that you're getting a lot of data and you're not reading it. So you're losing, basically, you're losing packets. So that's what that does. And what is the EER? Yeah, that one enables interrupts for these errors. This one enables interrupts for these events. And this one enables interrupts just for the TXT and RxNE. And you have to have this one and this one enabled if you want this RxNE interrupts. Right? You have to have both ITEV, IT event, and IT buff enabled to get your TXT and RxNE interrupts. That's reserved frequency. This is where you enter the frequency of not what you want your I2C to run at, but this is where you enter the frequency of the bus where the I2C is located. So if we look up at our maybe it's up here. I'm trying to find where it's gonna tell me about what bus this baby is on. It's usually some sort of diagram. Does this tell me the bus? Nope. Maybe it's my RCC. Oh Lord, I'm not gonna find the damn picture, am I? Oh, here it is. Okay, I2C 1 and 2, APB1 bus. So it's on the APB1 bus. So here you're gonna put the frequency that bus is running at, and the APB1 bus runs at half the frequency of your microcontroller, at least by default. So if you're running the F1 at 72, this baby is running at 36 megahertz. Okay. So you have to figure that out depending on what speed you're clocking your chip at. And I've been also thinking about doing the whole tutorial on how to adjust the clock and set everything, because everybody just tends to run it at 72 when you don't always necessarily need 72 megahertz. But everybody, faster is better. So yeah, so here you're gonna write 36 megahertz, and you're literally just gonna write the number 36. You're gonna shift 36 into this area, and that's it. When you're a slave, obviously you have to have a slave address. So if you set up your I2C as a slave, this is where you would write the address. And you can actually have two addresses. So you can have two slave addresses. Data register. This register is used for TXing, for RXing, and for sending the slave address that you want to talk to. In the newer microcontrollers by STM, there's a register for RX, there's a register for TX, and there's a register for the slave address. And there's a register where you tell it how many bytes you want to transfer, and then you just press start and it does it. But over here we have to do all of this in software because it's just one data register and nowhere to tell it how many bytes we want to send. Anyways, I'm sorry I keep promoting the newer chips because I really want to start just making tutorial on those. Anyway, so then you have here your status register 1. This, of course, all those errors and all these events that we enabled, this is where you're gonna see those flags being set. So when there's an arbitration lost error, this flag will be set and you're gonna read it in this status register 1. Whenever you send data on your I2C line, the next thing you're gonna do is put a while loop, and you're gonna sit there and wait until this thing is set, because this tells you that your data was transmitted. Well, not that your data was transmitted, but it tells you that the data register is empty and you can put more data in it, because the data that you put there previously is now in the shift registers. If you really want to check if your data was transmitted, it's this one, and that one is the byte transfer complete flag. This is your RX and E flag. This one will tell you that you've received data on your there's data waiting to be read in that data register right here. And this is that you have a stop condition. This has to do with 10-bit address. Byte transfer complete. When you send out, after you send out the start condition, you're gonna send out after you send out the start condition, you're gonna wait for this flag right here that's gonna tell you that start condition was actually sent. Once you exit that while loop because the start condition was sent, the next thing you're going to do is send the slave address, and then you're gonna sit there and you're gonna wait until the slave replies, and then when the slave replies that there's an address match, this flag will be set, and then you can move on to your TX or RX stuff. And I know, I'm sorry if this sounds all weird and stuff, but it makes more sense when you see it in the code. And here's your status register 2, where this is really more a lot of the stuff to do with the STM bus. For example, all of these. This one is if you're a slave. That means there was a general call. This is, I don't know. I've not even used that register. Oh, these two right here is the bus is busy. Sometimes it will get stuck in this mode. It did for me until I started using DMA, and then it just doesn't get stuck anymore. And this is where you actually set if you're in slave mode or in master mode. But if you don't even have to worry about this, because once you send a start condition, it puts it in master mode for you anyways. Alright, then you have the control register, CCR. Oops. This first bit, the clock control register, this first bit you're gonna tell, the 15th bit, you're gonna tell it if you're in standard mode or fast mode. Fast mode is 400 kilohertz. Anything below that is standard mode. The duty cycle for your clock, this mode right here is basically T low over T high equals 2, so that's a 2-to-1 ratio, versus this mode where it's a 16-to-9 ratio. I don't really know the difference. Not that I don't know the difference, but I don't see why you would use one over the other. So maybe I really don't know the difference. So I've never found the need to even use this. I leave that at default. Works fine for me. Maybe someday I'll encounter a reason to choose otherwise, I guess. I don't know. Clock counter. Okay, so here is where you're going to need your calculator. So let's do this standard mode, because that's what I did in my code. And I think I used 100 kilohertz. Alright, so maybe I should just go over this in the actual code. Yeah, I think I'll just go over this in the code. It's not that crazy, so don't even worry about it. But this is where you're gonna set the frequency of your I2C, and in my code I put it at 100 kilohertz. And it's not as simple as just writing 100 here. You have to do a little bit of math, but it's just division and multiplication. Anyways, and then this too requires a little bit of math, which is all right here. So if you want to try it yourselves, by all means, just have it read it this. But I'm gonna cover that in my next video, where we're gonna go ahead and get into the code. So yeah, so those are all the registers for the I2C, guys. Sorry if it seemed kind of rushed. I'm just, I'll be honest with you, I'm really annoyed at this I2C for this microcontroller. I'm gonna make some more videos on I2C using the other chip, the L0, and that is a thing of beauty. Nevertheless, so stay tuned for the next video. We'll jump into the code, we'll get it working, and even though I'm complaining of how annoying this is, once you do it the right way, how I'm going to show you, it's bug free. So it works, and stay tuned for that.